So, today we are going to discuss the Poisson and exponential distribution, and which is very important. Both of them are very important distributions, particularly in the context of the queuing system or waiting lines. In our previous class, we have seen that the most usual queuing system has this kind of assumptions: the Poisson distribution for a number of arrivals and exponential distribution for service time. But since both distributions are basically what is called, one is the complement of the other, that means if number of arrivals are Poisson distributed, then inter-arrival time is exponentially distributed, right. So, these are their connections. Now, how are they related? First of all, the Poisson distribution is occurring for any random phenomena that occurs on a per unit basis, like per unit area, per unit volume, per unit time. They are all well approximated by the Poisson process. Example: number of defective rivets in an airplane wing, spots per square meter of cloth, machine breakdown per week, number of misprints in a book, number of customers arriving per day, wrong phone calls received during a week. So, they are all different distributions, different examples of the Poisson process. Now, if you look at the details of the Poisson arrival, the Poisson arrivals could be deterministic or random. First of all, when arrivals are random, an usual assumption of the arrivals is the Poisson process, right. A Poisson process has the following properties. What are they? First one, orderliness. At most one customer will arrive during a given very small time interval. Suppose we talk about a small time interval delta t, then we expect only one customer at most will arrive during that very small delta t time, is it not? That is called orderliness. Second one is called stationarity. Probability that of arrivals within a time interval is the same for all time intervals of equal length. That is very important. That is that if we take two different time intervals, one is say 0 to delta t and another is t to delta t, right. So, delta t plus t, obviously plus t, or maybe another 4 t to 4 t plus delta t. You see, all of them 0 to delta t, t to t plus delta t and 4 t to 4 t plus delta t, all of them are different time intervals of equal length. For example, this could be 1, this could be 1, or this could be 1, right. So, all of these in this time interval, the number of arrivals that may happen will be similar distribution, right. So, the probability of arrivals will be same in all the three cases, that is called stationarity. So, that means if we have one, we can know the other, as simple as that. Finally, independence. Arrival of one customer has no influence on the arrival of another, right. So, that means sometime we think that within 5 customers have come in the last time period. So, this time period we may not get more, not like that. This time period also 5 may come, the 5 is equally likely like zeros, and this is the most important property. That is why they are called Markovian. They have what is known as the memoryless property. What is memoryless, etc., we shall look a little later. So, this is the Poisson distribution. Probability of x equal to n, this is Poisson distribution, Poisson distribution, probability of x equal to n equal to lambda t to the power n e to the power minus lambda t by factorial n. So, that is the the Poisson distribution expression. Now, let us say lambda is the average number of arrivals, in a given time. Let us say lambda equal to 6 per hour, right. And let us say that this Poisson process has been established for a time period between 8 o'clock to 9 o'clock, and we are talking about half an hour time between 8 to 8:30. So, what is T? T is basically half hour, right. For this period T, we are doing all these calculations. So, therefore, lambda T will be 6 into half equal to 3. Hour is our unit. So, we got the value of lambda T. So, what is the probability that nobody will arrive during this half an hour time? Probability that nobody will arrive in the half hour considered. So, probability of x equal to 0, sometimes it is simply written P0. So, P0 lambda t is 3 will be 3 to the power 0 e to the power minus 3 by factorial 0. Now, you see 3 to the power 0 and they are all 1. So, it all comes to e to the power minus 3, and e to the power minus 3, that value I have got here, that is 0498. So, what will be P x equal to 3? If x equal to 3, sometimes it is called P3. No, it should be then how much? Lambda t is 3, 3 to the power 3 multiplied by e to the power minus 3 by factorial 3. How much is 3 to the power 3? It is 27. How much is factorial 3? 3 into 2 into 1, 6. So, 27 by 6. How much is 27 by 6? If you cancel 3, then 9 by 2, or in other words 4.5. 4.5 e to the power minus 3, I have the figure here, it is 0.224, right. So, look at the slide once again. Customers arrive at a bank counter according to a Poisson distribution at a rate of 6 per hour. What is the probability that n customers will arrive in first half an hour, right. So, lambda equal to 6, t equal to half. So, lambda t equal to 3 and p n equal to 0 is e to the power minus 3, p n equal to 1 is 3 e to the power minus 3, and similarly we can do all these calculations. So, basically we can actually find the probabilities of the number of customers arriving at a particular service station with regard to the Poisson arrival process very easily, right. So, these calculations can be very easily done. On the other side, like arrivals, service also could be deterministic or random. When service process is random, an usual assumption of the service time is the exponential distribution. So, corresponding to the Poisson distribution, we can also think of an exponential distribution, which is given by f t equal to mu e to the power minus mu t. So, mu is the average number of customers to be served per time period, and 1 by mu is the mean service time, right. So, probability that the service time x is less than the time t is given by 1 minus e to the power minus mu t. So, probability that, let us write it here, probability that the service time x will be less than time t, that is probability of x less than equal to t is given by 1 minus e to the power minus mu t, right. So, this particular thing is given by what is known as exponential distribution. Exponential distribution. Now, looking further, probability that, so once again the same thing we are repeated, that service time x is less than time t is 1 minus e to the power minus mu t. So, if the average service time is 6 minutes per customer and service time follows an exponential distribution, what is the probability that it will take less than 3 minutes to serve the next customer, right. So, in this case what is it that we are going to take? So, we say here t equal to 3 minutes. So, 3 minutes is 3 by 60 hours equal to 0.05 hours. So, what is the probability of x less than equal to 0.05? It will be given by 1 minus e to the power minus 6 into 0.05, right. So, how much is that? In this case, 6 was the the service time was 6. So, basically mu was basically 1 by mu is 6 minutes. So, mu equal to 10 per hour, right. So, in this case not 6, it will be 10. So, this is equal to 1 minus e to the power minus 0.5, and this value comes out to be 0.3935, right. So, basically this is how the calculation goes. Once again let us look at the slide. So, if the average service time is 6 minutes per customer, then mu will be 10 per hour, that is the average service per hour, right. Average number of customers serviced per hour, that is called mu, which will be equal to 10 customers per hour. So, probability of the service time less than 3 minutes or probability of x less than 0.05 hours will be given by 1 minus e to the power minus 10 into 0.05 is 1 minus e to the power minus half, which comes out to be 0.3935. All right. So, you can do such kind of very simple calculations of Poisson distribution and exponential service process very easily. Now, look here, this is a little complicated, but very important slide, that is there are 6 key properties of exponential distribution. What are they? It is a strictly decreasing function. Second one, there is a lack of memory, or what is known as the memoryless property, that is why it is called a Markovian process. Since exponential distribution and Poisson distribution, they are very closely related, therefore, if one is having Markovian property, the other will also have the Markovian property. The minimum of several independent exponential random variables has an exponential distribution, right. Then there is a relationship with Poisson distribution. If number of arrivals is a Poisson process, then the distribution to inter-arrival time is exponential. And then for all positive values of t, probability of t between the t should be less than t plus delta t, given that random variable t is greater than t is lambda delta t for small t. And then finally, the distribution is unaffected by aggregation or disaggregation of the input process. Anyhow, let us look at it once more time. So, first of all, the first function, that is called the exponential distribution, that is there are strictly decreasing function. Supposing there are two equal intervals, right. In the two equal intervals, the p equal to, you see what is happening in an exponential distribution, you see this is the kind of plot that you get. So, the probability of 0, suppose this is 0 and this is delta t, this side is time. So, between these, in this area, this is the kind of probability distribution. And if you take another same amount of area between t and t plus delta t, then this area is less, right. So, this is what is we are calling as a strictly decreasing. So, look here, that is decreasing, that is the probability of the service time between this and the probability of this, this is how the comparison goes, right, that here it is high and here it is low. That is what it is called a strictly decreasing function. The second one, the lack of memory. The lack of memory essentially tells what? Let us look at the memoryless property, that is a very important one. So, here we are talking about a conditional probability. What is that conditional probability? That probability of t greater than t plus delta t, given that probability of t, I mean not like this, given t is greater than delta t, right. So, bracket closes here actually. So, see what is the probability of t greater than t plus delta t, given that t is greater than delta t. The thing is that memoryless property therefore says that does it depend on the period between 0 to delta t, because you see what we are telling, suppose t is here, now probability that this t is greater than t plus delta t, right. This is this is let us draw the diagram once again. So, this is our exponential distribution, this is delta t, this is t plus delta t, right. Then what is the probability that this a random variable t is a random variable, what is the probability that the random variable capital T is greater than, that means this portion, is it dependent on what has happened before, right. Given that it is already known that t is greater than delta t. That means, this period has already elapsed. Once this period is already elapsed, essentially the good thing is that when we try to find out this probability, that probability of t greater than t plus delta t given t is greater than delta t is nothing but p t greater than t. Right, p t greater than t. So, in other words, that it is not necessary that we have to really think of this. So, let us take an example. Suppose nobody has arrived in let us say first 10 minutes, right. So, what is the probability that somebody will arrival in the next minute? So, should we take the fact that nobody has arrived in the first 10 minutes, right? This fact is not required. That is what is the memoryless property all about, that we have to only take that last minute, that this between 10 to 11 whatever has happened, that is the only consideration here, right. Now, therefore, the proof is also here, that you can see that left hand side, that probability is t greater than t plus delta t is given by e to the power minus mu t plus delta t, and the other one is e to the power minus mu delta t. So, when you calculate, then you will find e to the power minus mu t, right. So, that is the RHS. So, that is the memoryless property all about. Let us look at a particular example, right. The example is find probability of 2 or more arrivals in 1 hour when the number of arrivals are Poisson distribution with an arrival rate of 2 per hour. So, here you can really calculate this from a simple addition, that probability mass function here is lambda t to the power x e to the power minus lambda t by x factorial. So, that is the Poisson distribution. So, what will be the CDF or cumulative distribution function? It is sum over 0 to x lambda t to the power n e to the power minus lambda t by factorial n. So, what is the arrival rate? The customers are arriving at a rate of 2 per hour, that is lambda equal to 2 per hour. From the Poisson distribution, we get lambda equal to 2 per hour, t equal to 1 per hour, therefore, lambda t equal to 2. So, what will be the probability of 0 arrival? P 0, that will be given by this sum 2 to the power 0, because that is the lambda t, then e to the power minus 2, e to the power because that is what is the value of the lambda t, and then we can calculate by factorial 0, that is e to the power minus 2 is coming to 0.135. So, what is the probability of 1 arrival? P equal to 1, that is given by again lambda t to the power n e to the power minus lambda t by factorial n 0.271. Hence, the probability of 2 or more arrivals in next 1 hour, that will be given by 1 minus P 0 minus P 1 equal to 1 minus 0.135 minus 0.271 equal to 0.594 equal to 59.4%. Let us look at it in a slightly more detail. See what we have got here, that we have a Poisson process. In a Poisson process, we have the P x equal to lambda t to the power x e to the power minus lambda t by factorial x. So, this is the Poisson process. Now, what is the CDF? CDF will be, this is the PDF, the CDF will be that f x equal to, because this is a discrete process, So, f x will be sum over 0 to x x. Now, here we know lambda equal to 2 per hour and t equal to 1. So, lambda t equal to 2 into 1 equal to 2. So, already we know lambda t. So, what is P 0? P 0 will be this one 2 to the power 0 e to the power minus 2 by factorial 0. So, it comes to e to the power minus 2, right. This value is already known, 0.135. What is P 1? P 1 is 2 to the power 1 e to the power minus 2 by factorial 1 equal to 2 e to the power minus 2. This value comes to 0.271 actually because of rounding of errors. Similarly, P 2 will be 3 to the power 2 to the power 1, that is P 2 e to the power minus 2 by factorial 2 equal to it will be again 2 to the power 1 again 2 to the power 1 by 2. So, it also will be same 2 by 2, that is e to the power minus 2 equal to 0.135, right. So, you can see that so it will be 2 to the power 2. So, this also will be 2 to the power 2, 4 by 2. So, 2 e to the power 2, this also will be 0.271, right. So, one interesting thing that is to be noted here, that number of 0 arrivals is 0.135, single arrival is 0.271, probability of 2 arrivals is 0.271. So, what is the probability of at least 2 arrivals, right, probability of at least 2 arrivals. Here, because there are 3 things, that probability of 0 arrival, probability of single arrival, probability of 2 arrivals, right. So, it could be equal to P 0, it will be P 2 plus P 3 plus dot dot dot, that is equal to 1 minus P 0 minus P 1 equal to 1 minus 0.135 minus 0.271 equal to 0.594, right. So, similarly, you can do all these calculations, probability of at least 1 arrival, right, or 1 arrival or more. So, this is let us make it last one, probability of 1 or more arrivals equal to P 1 plus P 2 plus dot 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 equal to 1 minus P 0 equal to 1 minus 0.135, right. So, equal to 0.865, that is okay, right. So, like this what we can do, we can calculate such kind of things from Poisson process or exponential process, and we can make some what you call conclusions out of them. So, right. So, thank you very much.